13. Organic chemistry. We're going to talk about carbon compounds, bonds and types, petroleum products, organic molecules and the structures, formulas and structure, organic compounds, groups and polymers, chemistry of life, the molecules important for biological processes, carbon compounds. Organic chemistry is the study of the carbon containing compounds. So organic chemistry is classified as the study of carbon and carbon containing compounds. Why organic chemistry is important? Organic chemistry constitutes a separate branch of chemistry. So why is it so special that it needs to have its own dedicated wing in the chemistry? Because we are made up of carbon. Over 90% of all compounds contain an element carbon. There are over 3 million known organic compounds and over 100,000 are added every year. On contrast to that, only about 300,000 inorganic compounds are existing so far. Now you can understand why it is so important to learn about organic chemistry and why we need to dedicate a full branch for organic chemistry. Now we are going to talk about the difference between organic chemistry and inorganic chemistry, or organic compounds and inorganic compounds. Organic compounds are the compounds which contain carbon. Inorganic compounds are the ones which do not contain carbon. Interesting about organic compounds is until around 1850, scientists believed that organic compounds could only be formed by living things. They even considered organic compounds to have some vital force associated with life. Then came Mr. Fowler, successfully formed a synthesis reaction in which he did ammonium cyanide heating, and he came up with the urea, that is a primary ingredient in urine, which is also used as a fertilizer for the fields. So then he could find out that this is not only a naturally existing material, but also we could make it artificially too. So after Fowler, the demonstration of many natural organic molecules were produced by chemists. Then organic molecules that do not occur naturally were produced at an even increasing pace. Organic chemistry is very important because organic chemicals are being introduced into the environment at an astonishing rate. Organic chemistry has implications to a wide variety of fields of study: medicine, biological sciences, agriculture, civil engineering, water management, etc. Why carbon is so unique? Carbon atom can form bonds with many other molecules. The carbon atom forms a variety of different bonding structures. Carbon atoms form 4 covalent bonds with each other as well as with others. So it shares the electrons between the carbon and any other element to form a bond and to come up with the compound. We have already seen that covalent bonds between carbon atoms can result in vastly different structures. For example, graphite and diamond. Diamond is the hardest material and graphite is very fragile. So even though they are both carbon compounds based on their bonding between the atoms, the structure of it is a little bit different. The position of the carbon atom in the periodic table is a clue to its versatility. Carbon is located midway in its period. This means that the outer electron shell is half full. So as you can see in the picture, that it has 6 electrons, and in its valency it has 4 electrons. Instead of gaining or losing electrons, carbon has a natural tendency to share electrons in order to complete its outer shell. It needs 2 more in this shell right here. It has 2 in the first S shell, and it has 2 more in the P shell. It needs 4 more in order for it to be complete structure, complete filled structure. The unique bonding ability of carbon extends to the bonds with other elements as well. Those that contain only carbon and hydrogen are classified as hydrocarbons. These are very simple structures, very important variety. We depend strongly on the chemistry of the hydrocarbons. Carbon compounds. The general properties of carbon compounds are, most carbon compounds are non-electrolytes. The reaction rates of carbon compounds are usually slow. Many carbon compounds oxide slowly in air but rapidly if heated. Most carbon compounds are unstable at high temperatures. Alkane group. This group of hydrocarbons include many familiar gases used in everyday life. Some of the members of alkane groups: methane, ethane, propane, butane, N-pentane, octane, and so on. All the natural gas used in the household purpose consists of several alkanes. Primarily, it has methane in it. About 80% of the natural gas is methane. The crude oil is the basic raw ingredient of the production of useful petroleum-based fuels. This natural resource is a combination of several alkanes. As you can see here, if you have a barrel of crude oil, you have all these things from as byproducts from this, as products from this crude oil: gasoline, diesel, jet fuel, and petroleum, asphalt, boiler oil, and so on and so forth. With those 5 plus carbon atoms, the natural gas is this natural resource is a combination of several alkanes. Those with 5 plus carbon atoms, and the exact proportion of each alkane depends on the source of the crude oil. Distillation. In order to effectively use the crude oil, some alkanes must be at least partially separated from the rest. This is a difficult process. Since the physical and chemical properties of the members of the alkane family are very similar, the solution to this problem is found in the process of fractional distillation. So, they clean up. Distillation, as the name indicates, it's a cleaning process. And how they do is they make it into fractions. In the bit of it is cleaned, and again next bit of it is cleaned, and next bit. So fraction of it is cleaned in every step. Fractional distillation refers to the production of the several hydrocarbon compounds made possible by thoroughly understanding the detailed properties and small differences between each of the compounds present in the crude oil. As we have seen already that each crude oil barrel consists of gasoline, diesel, and other products. So based on how you understand the properties of these materials, you can distill them clearly. The crude oil is heated. At each increasing temperature, some of the alkanes will evaporate. So as the crude oil has different types of oils in there, but everything has a different temperature. So it will be keep on heated, and based on its own temperature, the that particular product would be evaporated. The vapors are collected and further refined to separate the multiple compounds that may be present in the vapor. This requires a specially designed engineered tower. So, the natural resource, which is a crude oil, is a complicated structure of hydrocarbons composing of the varieties depending on its source. Each hydrocarbon has a different boiling point temperature, varies according to the number of carbon atoms, their molecules, and how they are arranged. Fractional distillation uses the difference in the boiling point and vaporization points to separate the hydrocarbons present in the crude oil. So this is how the crude oil distillation tank looks like. So at the bottom, they start heating, and this tower has the high temperatures at the bottom, low temperatures as they go high. So they keep on heating it up, and once they start evaporating based on their own temperature, something like gas oil evaporates at 250 to 350 degrees Celsius, kerosene from 200 to 300, gasoline from 40 to 200, and petroleum is less than 40 degrees Celsius. So as you keep heating, let's say 40 degrees Celsius, once it gets to 40 degrees Celsius, the petroleum gets evaporated. So it keeps on going up, and once this goes high above, when it gets to its so it is still high here, so it keeps on going up and evaporating. Finally, when it gets right here, it is cold temperature, then it's evaporation temperature, so it gets kind of hardened, and then it will be collected in this area. And then next, let's say if we have the gasoline in the crude oil. So the gasoline, it evaporates between 40 to 200 degrees Celsius. So once the temperature here at the bottom is 40 degrees Celsius, then it keeps evaporating, and once it gets at this location right here, because it is the temperature where it would get which is less than its boiling point temperature, so it will be collected right here. So in the similar fashion, so in every segment, all these things are collected. Several steps are required to produce fuels. So this is how the fuel will evaporate, and it will be collected in each segment. Engineering the tower. The fractioning column, a tube that is cooler at the top than the bottom. The boiling vapors cool as they rise. Vapors condense onto a tray when they reach the part of the column which is cooler than its boiling point. Reactions involved in this tank. The catalytic cracking. Large hydrocarbon molecules composed into smaller molecules via the introduction of catalyst. It requires pressure. It requires catalyst assistance too. Polymerization. Small light hydrocarbons synthesized into larger molecules. More catalytic cracking. Cracking is the name that is given for breaking up large hydrocarbons into smaller and more useful bits. It can be achieved in two ways: by using high pressure and temperature without catalyst, lower temperature and pressures with the presence of catalyst. The useful catalyst. The catalyst is not unique. One common catalyst is a small zeolite crystal. Zeolite is aluminum silicate mineral, and the catalyst hydrocarbon mixture is then blown into a reaction chamber at a temperature of about 500 degrees Celsius. This is called fluid catalytic cracking. The catalyst solid remains in a different phase than the liquids to be separated.